Okay, everyone, good morning. Welcome to the week 7 of the BRICS Idea Data Analytics program. It's been a long journey, and to be honest, congratulations to each and every one of you. Congratulations to all of us here for pulling this off after a long trial. I'm not sure how many people are here. Let me see. I think we are up to close to 50. Yeah. I remember the first time we started this, we had over 400 people join the section, but now I know people have tired, a lot of people have went out. Again, this is not an easy task, but the good thing about this program is that all the resources are available for you to continue at your own pace. So in order not to waste a lot of time, this morning we'll be talking about machine learning again and just completing the section, the part that we didn't talk about last week. Now, even though we are not going to be so exhaustive in this lecture, we just want to give you a bit of idea on how to get started and also play around and begin to get the idea of machine learning and how to go from where to where. I'm going to start the section on classification, just using the supervised learning classification method, and then Priya and Najam will take over on using doing deep learning with image classification. They are going to do a bit of introduction and one bit of dimension reduction process. So anyway, let's just hop in because we don't have a lot of time. Last week we started with machine learning. We looked at the criteria for machine learning, use cases in astronomy when it is relevant, and also shared a bit of materials, PDF files that could guide you on the explanation behind or concept behind machine learning, as well as when it is useful, the flow, how to go about it, how to collect your data, clean your data, perform analysis, do your modeling, do your evaluation, do your testing, and the rest of them, and validation. So the last week we highlighted more of regression. We managed to do a regression problem using real data set in astronomy. So this week, I want to rush you through a hands-on on doing classification. You're also using real data set in astronomy. If you're seeing my screen right now, you're going to see this notebook in the week 7. This notebook is already there in GitHub, so all you need to do is to load it on your PC, and then you can get started and run it. So what we did here is to collect astronomy data sets. So it's not like it's a very short notebook, but this just tells you that you can start from somewhere and then you fly. So we've talked about VISIA a lot. The CDS VISIA is an astronomical archive where you have tons of data sets, catalogs from surveys, research, and the rest of them. And we've played around using AstroQuery, which is a Python astronomy package for data query and collecting data from archives and tap services from across the world. So in this notebook, you're going to see how to collect data from VISIA, and these data sets have been used for this machine learning. So what it means is that you don't need to go and start looking for some data somewhere or maybe some nicely clean data. You can actually just look for scientific interest and then you're jumping. So this notebook here is the notebook that will basically describe what we want to do. This is a classification exercise, and this introduction basically gives you an idea of what needs to be done and the rest of them. So, but in any case, let's quickly run through the data query section. Many of you have heard about the SDSS. SDSS stands for Sloan Digital Skies Survey. It's a spectroscopic instrument in the US. One of the most ideal instrument for spectroscopy. They collect They have millions of data sets of both stars and galaxies, hundreds of millions of data sets of stars and galaxies that have been observed within the northern sky. And this data is released concurrently. I think we are in the DR17. I can't remember exactly, but you can quickly go. So they've been releasing data release 1, 16, 17. But I think the data used for this work, we're going to use the DR16 data set. Now, let's just quickly take a look at Visia. Here, you can see you know what Visia is. So like I said before, Visia is an archive, it's an astronomical archive. So this is the UI. We can quickly just do a quick search of SDSS. If you come here and search for SDSS find, it's going to show you there are not so many SDSS data sets. Almost half of them are obsolete. The other half are available for you. So we can see that we do have two data sets, latest data sets. This is the one, the release 16 is I think is the latest here. And then that is the latest data set on Visia. I think if you go to their own website, you should be able to find newer data sets. But for Visia, they do have these DR16 data sets here by Ahumada plus 2020. The other one is the SDSS Quasar catalog, also from the data release 16 and by like 2020. So if you hop in here, let's open this. You'll be able to see the information about this catalog. You can come to the README here, and then you will see the information. It says this paper document the 16 data release of SDSS, fourth and penultimate from the fourth phase, blah, blah, blah. You can read through. You can see the whole sky region where this data have been collected. You can see it does take a patch of the this image you're looking at is definitely the galactic plane. This is in galactic coordinates. So you're seeing that a large chunk of the northern hemisphere have been observed. A portion of the southern pole is also observed, and some patches of the sky that crosses the galactic plane, but it's not so many. You can see that this region is a bit void. This is mostly southern area and the rest. So, but then if you want to see the information about the table itself, you come here and then you see this table. And this describes what the columns are for you. Because like I said, the one good thing about machine learning is that you need to understand the domain. Domain means that you need to understand the context, the science behind the data. It helps you a lot. So this data has roughly 469. It says it has 469 million primary sources plus 325 million secondary sources. You can see this is definitely a huge data set. And then it does contain mostly photometric information of the source. I think what they released there is mostly the photometric and spectral information because this is also collecting spectroscopy. So they are measuring certain lines. And then, well, there are key things that you need to pick here. The coordinates, the class of the object. They do have whether it is a star, a galaxy. If it's a star, it's 6. If it's a galaxy, it is 3. And the magnitudes are also marked. So there are some default columns that are already marked here. These are like the primary ones they want you to like pay attention to. This is the magnitude, the AB magnitude of this survey. And it does have 5 magnitudes, UG. These are all optical magnitudes, optical filters. You don't have the spectral type, and then which is indicated here. Okay, this is a spectroscopic class, galaxy, QSO, star. You have the red, you also have the redshift information, the photometric redshift. I think I've seen here, look at it here, photometric redshift. So you can take your own time to look at this. So this data can be used in multiple shapes or form. If you're interested in maybe getting the spectral information, I believe when you go to their archive, their personal web archive, you should be able to find data sets, maybe the spectral information. But instead of wasting a lot of our time, let's hop in back to our notebook. So information about the paper is of the paper, the Ahomada paper is you can find it in this link, NASA ADS. You should be able to find either the published paper itself on their website if you have access, or you can also get the or you can also so you can come here. If you're not able to access this is the link you can use to access the paper. If you're not able to do so, you can check out the preprint. The preprint is free, so you can access it even if you can access the first ones here. Yeah. So, okay, back to business. What did we do? We used Astro Query Visia function. We imported the Visia from Astro Query Visia module. We also imported AstroPy table VStack. You understand the reason why. So this data is very huge. And because it is huge, what it means is that you need a large compute resource to query it. But unfortunately, my computer is not that heavy. I also believe that yours will not be also that computationally heavy to handle it. So what we did here was to select interested columns. So if you come here, you will see these columns here, RAICS. So these things were a handful of them were selected. So mostly the default ones were selected, not all of the default ones anyway. We selected them. And then that is why you can see the columns here, codes. So this about roughly, I would say, probably 11 or 12 columns were selected. And this is the catalog ID. How do you know the catalog ID? You come here, this information here, this is the catalog ID, this one here, V/154/SDSS16. This is the catalog ID. So taking the catalog ID, we come back to this notebook, and then we already define the columns that we're interested in, call the Visia function here, and then pass in the columns, pass in the catalog ID, limit the number of rows that we want to query because this data is huge and we feel like, okay, you can start with 150, 200. You can depend on your capacity. So the thing is, if you do not put in this is going to return only 50 rows for you. So the row limit is you telling the function how many columns it can query and return for you. So in the spectral class, we have three spectral classes there, which is more like the type of object, the galaxy, QSO, and star. How do you know this? If you come to this column here, there's a column here towards the bottom called, where is it again? Come on, eyes are failing me. So this one, SPCL, it said spectroscopic class, galaxy, QSO, and star. So galaxy QSO are extragalactic objects. So galaxies QSO, I think, is the kind of more like the compact region of the galaxy, or more like the central part of the galaxy, usually very bright like a star. It kind of looks like a compact object, but it is not a star. And it's the star itself. So I used to just select columns that have this information, rows that have this information, because not all of them do have this. Just more like trying to do a bit of tidying, data cleaning. So query this, galaxies, QSO, stars, and then stack all of them together. There's a function in this query, there's a way to also pass all of these informations together, but for some reasons, it wasn't working. Maybe you can try it in your own. You can check out, maybe read more about Visia and see if you can be able to pass that. But because of time, we have to manually do it. And then VStack means I want you to stack all of these things together. So there's a H stack, there's a VStack. VStack is an AstroPy table. It says when you have three different tables of same column types, you can vertically stack them together. Yeah, horizontal means you want to stack them horizontally. So we're using the VStack, and then we'll stack them, and then we have this data set. And then you can see it return 450,000 rows. So you can see this data is quite huge. And because for each of this is going to query 150,000, 150,000 each. And then we have this. Now, after doing this, you can save it as CSV file. So this task has been done already. This is saved in data. If you come here, you will see it just tells you 16 minutes ago. It does saves this data here, roughly about 443.6 megabytes. You can see the data is huge. So this is just showing how we can move from A to B, just like that. You get so it's quite interesting. The beautiful thing. There are a number of things you can do with this data. You can also plot the coordinates, and then you will see how it looks like in the sky, the regions of the sky where you've collected this data from. You can also take a look at the MJD. Some of you, if you've done the time series, you can probably see this is the time when these observations were taken. And the rest of them, you can also compare the magnitudes. But moving forward, let's look at the classification exercise. So what we have here now is that we've had we have observations for 450,000 sources. It might look huge, but in astronomy, that is not large. That is not a large number. So, but at least it's something that you can start with and get started with and play around. So our objective is that we have this information, photometric information, redshift information. And then the question now is, how can we use this information to predict whether the source or the target is a star, is a galaxy, or a QSO? So what it means is that you can choose to do a binary classification, which is one of the type of classifications. So in a classification in supervised learning, we do have basically two types of classification. Binary classification, when you are dealing with just two types of objects or classes or labels, or when you have more than two, in a case where now you now have maybe three or anything above two. So yeah, and in this case, we have three classes. In the class column, so if you can choose to do the binary classification, which is one exercise that I hope you guys will do at your own convenient time. Try out, you can start with the binary classification. But let's look at the multi-class classification. So this is just here showing you a description of the relationship between the magnitudes, the fluxes, and all that, and on how by magnitude filters, the observations, measurements have been derived. And then we get started. I'm not going to spend a lot of time here. I did talk a lot last week about the whole methodology behind scale support scikit-learn, how to import it, the different types, whether you're doing regression or you're doing classification. So we're going to be looking at classification today. So we import a number of the things that we need for our data sets for analysis. Here we install the pipeline package, which is a efficient tool for managing a couple of processes in scikit-learn. We did talk about scaling, feature scaling last week. Feature scaling is a way of you balancing your data set. If you think your data set is skewed, how can you balance it in such a way that you make it close to normal? How can you normalize it, or how can you scale them in such a way that they are a bit uniform? Because it helps a lot when you're doing machine learning. And then these other ones are tools that we are using: cross-validation, predicting, train test plate is used for training, and it's more like using splitting your data set conveniently. And then these are the couple of metrics that we are using. These are a handful of the classifiers we are going to try out. So what do? We load the data set. Let's run this. We load the data set. So this is a CSV file. For you to reading CSV file is not a peculiar task. We have been doing this since week 2 of this training. So we load the data sets, and here we are. So you can see here, this is the information. And we can play around a handful of things that you can do, which we usually call this exploratory data analysis. You don't just load data and then you start using it. You need to do some inspection. Just like if you load data in Excel, what do? You try and look at the columns, check if there are missing values, check if there are missing values. You also check whether there are a bit of skewness or outliers in your data set, or things that are a bit off. So easiest thing to do is to look at the shape. If you do this, it's going to tell you how many number of rows and how many number of columns. So it tells you they have 45,000, 450,000 row data sets, data points. And you have 13 features. But anyway, we're going to see that we will not be needing all of the 13 features. And then info quickly tells you, gives you information about this data set. And as you can see here, it's telling you that for majority of the columns that there are no null information. For majority of there are no null information. So this is quickly will tell you, okay, what? So it means in this case, let's look at I magnitude. So in I magnitude, you will notice that there is only one source that didn't have the I magnitude information. You see, that's weird, but a majority of them are quite clean. For the subclass, you see that close to half or more, just a little over half of the data set do not have the information. For Redshift, you will see that less than half of these data sets have photometric redshift information. So this is where it becomes dicey, which now depends on the use case or the information of the column or feature. If you think it is relevant, then you can play around, do selection for the data that you think is ideal for you, that you want to use for your machine learning. I do know a bit about this data, and then all I can tell you is that we will not be using things like the object ID. Object ID is more like in the ID information. This is not going to add any value to our data set. The coordinate itself will not help us because we're not looking at their positions. We don't think positions matter in the kind of classification that we want to do. Class is also very useful if you want to do binary classification. The class is only when they say a galaxy or a star. But we choose to use the spectral class, class information because it gives us 3 classifications. So these other ones are the photometric information. The MJD itself is just the time the observation was made. So it's not going to be useful for us in this exercise. So based on the fact that the redshift information, we need it for this project, we'll have to select only data points that have spectroscopic information. Now that we have done this, we can additionally also run this again to see the information, to see how the information has changed. Remember, the raw data is sitting on disk, so doing this is not going to change the raw data you already have in disk. It's only going to be the one loaded in the notebook. So here you can see we now have 162,516 rows. It's still enough data point for us to do our analysis or do our machine learning modeling. And then they're quite in the whole, the data type is quite the way we want them to be. So nothing is of different here. So here we look at the spectral classes. You can see galaxies. Here we are saying, I want you to look at this class, spectroscopy class, and tell me how many number of how many times galaxies appear, QSO and star. You can see star is the lowest, just less than 9,000 stars in this data set. We have over 440,000 galaxies. We have close to 13,500 QSOs. So this is beautiful. Now we'll make a plot of this data. And then when you make a plot of this data, you can see that galaxies are quite high compared to the other classes. Now, what happens there is a case where this is what we call imbalanced data set. So imbalanced data set is a case where you have a class information or category or labels, and one type of the class dominates over the other. So in this case, um, you can tell that galaxies dominate more than 80% of the data set, while QSO and star makes up probably um, less than 20% of the data sets. So what does it tell you? Machine learning is very beautiful when you have the data set is a bit balanced. Places where classes are more like almost the same or closer to the same. They probably will not never be the same, but yeah. So we could have choose to neglect the spectroscopic the redshift information, but I just want to bring this idea for you to also see that depending on how you want to go about doing the machine learning or classification, it can be a bit different. So now, looking at this, uh, what do you do next? Um, should we get worried? Well, the answer is no. It depends on how far you want to go. A couple of things you can do is to use the SMOT methodology. There's something called SMOT in machine learning that can be used to handle imbalanced data sets. Yeah, or you can do a quick Google. Let me see if I can find it here. We're called, you can say how to handle imbalanced data sets in machine learning, classes in machine learning. So you can see a couple of examples here. You have, I think I've read this before by Analytics Video. They do have a very nice, you can see it's showing you some examples on how to do this. Mostly there are a couple of things that you can do. You can choose to maybe do sample selection. So you can do a bit of sampling where you just select, okay, given that I have, oh, sorry, I'm not sure what, okay, so keep reading. Yeah, anyway, so this is not our point. So you can basically do this. So there are a couple of ways to handle this, which is you can choose to now sample the data set. You can choose to say, you know what, let's select roughly the same number of size as a QSO or star from Galaxy, and then drop the remaining ones and then use it for this training. Or you can do a bit of what to call oversampling and undersampling. So I think oversampling is where you now try to randomize the minority classes and bring them at par to the majority class. Or you undersample, which means you can filter off from the larger class and bring the size to that of the lower classes. So it can go this way. You have a Python tool called SMOTE, SMOTE, for doing this very analysis before you can proceed into training your data set. But we choose not to do that anyway. Yeah, you can take your time and see how to do that yourself. Choose not to do that in this exercise. But I just wanted to mention it to you so that you'll be aware. Now, I remember I told you there's something we call based on the fact that we have this information. And remember last week when we were doing regression, what did we do? We predicted the redshift information. So we used the colors of the stars to predict the redshift information. Oh, sorry, the colors of the objects to predict their redshift. So this time around, we are using redshift, we're using the colors. So we want to also use the colors. This data came with the magnitudes only. We do not have the color, but color is easy to do. Color is just simply taking the differences in the different bands, and then we'll have a new column. So if we do this here, we will have this. So what it means is that we have created 4 new columns, which is just the difference in the magnitudes and the bands. And then here you can see these informations here, U minus G, G minus R, R minus I minus Z. We did this last week, so I'm very sure this is not new. And since we know we want to do a classification problem and we are interested in using this as our label, so what we're going to do is that we're going to create a new column called label. Now, what label is going to do is that already we know that we only have three classes in this data set, Galaxy, QSO, and Star, but we want to encode it into numbers. So where we know that maybe 0 represents a galaxy, 1 represents a QSO, and 2 represents a class. So this is what we do here using the label encoder. So you initialize the label encoder and then use the fit transform from the function to apply it to the object that you want to encode. This is very simple. So here we do this. And then you can see it now says Galaxy is 0, QSO is 1, and Star is 2. So now when we run this again, okay, what we do here, sorry, let me do this instead. Apologies. Um, okay. So yeah, just convert this to integer 4 and then run the describe function. So the describe function is one of the tools you use when you're doing your exploratory data analysis. So it simply does the basic statistics for you. Runs through your columns, pick out the ones that are of numeric type, not object type. So whether it is a float or integer, it picks them up and performs the whole statistical summary for you. So what it means is, if you look at this, I did not select the columns that I wanted to describe for me. I only just said describe fully. It went through all of the columns and only selected the ones that are of numeric data type. So object ID, this is irrelevant. Coordinates, which is not going to be that useful for us, but you can see the right ascension region of the data set you collected for those who understand coordinates in astronomy. So in your equatorial coordinates, just like you have when you are doing the description of coordinates on Earth, Cartesian coordinates, we do have what we call the longitude and the latitude. So longitude runs from 0 to 360, right? And then the latitude can be up or down, 0 to 90, and 0 to 90, and 0 to minus 90. So things like that, or minus 90 to 0. That's for those in the south. So we do also have this in astronomical coordinates. So we have either it is galactic coordinates or whether it is equatorial coordinates. It's all, we also have this kind of behavior. So the right ascension is more equivalent to the longitude, and the declination is quite equivalent to the latitude. So what you're seeing here is that you have roughly between 5 to 180 degrees longitude, right? And then in the declination, it spans between 0 to 72. So this basically tells you that you're in the northern hemisphere. This basically tells you that the portion of the sky where you've collected data from. So what it means is supposedly you draw a Cartesian coordinate using the equatorial. It's mostly sitting in the um, in the top left. Yes. So okay. Let's also um go forward or move a bit fast. Here we look at the label that we have described. We look at the value classes, and you can see nothing changes. Also like what we did initially for the spectroscopic class. And then after that, we'll now try to do a bit of visualization. We know what we have here. We do not have a lot of columns. We only have the magnitude and the colors which we have generated. What we want to do now is to do a plot to see the distribution, right? And we can quickly do that. This is basically I reuse the same code we used in the regression exercise last week. So if you've run through that, you will see that there's no difference here. It's basically the same thing. The only thing that changed is the variable name. And if we run this, we should be able to now get this. So you can see you have different distributions for the magnitude. Yeah, okay. You can see a couple of them. I would say they are kind of bimodal in shape, though they are all clustered together, so you will not be able to see, but you can still look at see the distribution for the 5 magnitudes. And then this is the color itself. In a few cases, we have those that have a bit of weird color, which is something that I'll probably recommend in your cleaning. If I'm you, this is just a demo that we are running now, but I'll probably just suggest that in this kind of example, especially for the colors, maybe you can now filter and say you don't want objects that have these weird colors because they might bring in a bit of confusion in your machine learning. Because you can see there are very few. Probably maybe it might be that there's something weird in one of the in the measurements. Yeah, but man, this is quite large from -10. You can probably just limit it to just things like say 5 to -5, or you can say okay 7 to -7 and things like that and go. But we did not do that. Like I always said, machine learning is a bit of exercise. So this is the redshift information. You can see the redshift is a bit this is not bimodal, this is more like 3. You can see there's a bit of 3 yeah, about 3, 1, 2, 3. Yeah. So this could be telling you something. We have 3 classes of objects, right? So it could be that this is actually just showing you the distribution for or where this classes their typical redshift. To be honest, I do think that this is stars, but this is not just star. It does also might contain a couple of other things there. Yeah, I know stars will fall in here a lot because stars do have low redshift. They are not that distant compared to QSOs and galaxies. So the galaxies are dominated here. Galaxies and QSOs, you always see them around here down. So okay, we move forward. Here we know the object that we already understand these data sets and we know the columns that we're interested in. Or okay, I'm just inferring this. Probably you need to do a bit of exercise. This is where domain knowledge comes in. We're interested in photometric information. That's all, and the redshift information. So I define these as features and label. So features just say, I'm only interested in these columns and this data moving forward. And we define this, and then we run a bit of heat map distribution to see how these data sets correlate. You can see a good number of them are correlated. A handful of them are also not correlated. How do you know this? This is the scale. This is the color map scale. So let me see if I can use this. Good. This is the color map scale. And then you can see for let's pick one. We have UMAG here, and UMAG and GMAG are a bit correlated. About 0.81 is highly correlated. RMAG and GMAG is also highly correlated of 0.96. So this just shows you the correlation information for the data set. Some of you may have done this in the past. I think you've done it in one of the exercises in statistical analysis. Okay, the diagonal value just tells you the correlation between a column and itself. So that is why it is always 1. The correlation of the same variable always give you 1. So put that at the back of your mind. So a couple of others are not that correlated. Especially you can see these ones that are a bit negative. You see, it's just telling you there's no correlation. Yeah. This can be a bit can give you ideas on what you need to do to maybe get a number of things, read them off your data. But we're not going to dwell on this right now. Next thing, so let me look at the time. Wow, time is moving very fast. So now we select our columns for X and Y. Let me increase this again. Good. So we select our columns for X and Y. We select our X. Remember, I told you this is usually a standard, not a must, but it thinks it helps a lot to understand that just like you know in the relationship, the function of X and Y. So you want to predict Y, right? And then Y is dependent on X. So more like a function of X that gives you Y. So we select our X columns, our X information and Y information, and then use the train text plate, which we did last week, and then test size of 20%, and then we're good to go. We don't have our data train and text plates. So here, you can see the train information. The train information is just showing you the columns that we've selected. It tells you that there is about 130,000 rows. Remember, out of the 162, it means 130,000 have been reserved for training, and then the remaining one, probably 30 something, will now be used for testing. And then here is a bit of the pipeline function that we have defined alongside the metrics that we want to calculate from this data set. Accuracy score tells you how well these how accurate your prediction is. Precision score tells you how precisely it is predicting the information. So what it means is how many times that in all of the time that it predicts star, how true is it a star? Is it actually accurate, or is it falsely classifying it as a star? Blah blah blah. So this is also applicable. We think this whole information have been listed last week and also talked about in the notebook. So I'm not going to dwell on them. This is a function. You can reuse this actually. This is how I like to define my functions because it helps me a lot in dealing with, especially when I have multiple algorithms that I want to test. So we run this and it's going to do a couple of things. It's going to run through the training, evaluation, and also doing the plotting so that you can quickly see how it looks like. You have defined set of classifiers, and we're not doing a bit of complex hyperparameter tuning like last week, but I'm going to ask you to do that later. You can use the same method we used in the notebook called hyperparameter or parameter tuning. Try and use it to replicate this for yourself. Now we can start training this. So if you start training this, let's see. This will take a couple of time because it's going to do a handful of things. It's going to use the standard scaler to scale the training data set. And then it's going to do a bit of cross-validation. And after that, it's going to fit the whole data set. And when it's done with it, it's going to calculate the accuracy, give you the classification report. And for classification, we tend to have some functions, algorithms tend to have feature importance, tend to tell you that in this classification that you have done, these are the features that contributed mostly in this prediction. So this is going to take a couple of minutes. I'm not sure if we can maybe here I'll try and round up because it's just going to run through. We have the random classification, we have the logistic regression, we have decision tree, we have k-nearest neighbor, we have the support vector classification. So these are basically the same set of algorithms that were used last week. The only difference this time around is that we are doing it for classification. We are not doing it for regression. Yeah, so this will take some minutes, I think, probably. This will probably run up to 20 minutes and we don't have the whole time. So the notebook is already there for you, well prepared. And it's going to give you this, but I think I need to stop here. It's almost, okay, maybe 9:45. Let me see. I know Priya is supposed to get on the other ones. So we should not spend a lot of time here. I think Priya can come in now. Um, I just hope this, I was hoping this one, the random forest one will be a bit fast so that you can see the first results and the plots for yourself and you can appreciate what has been done. Yeah. But notwithstanding, this take is going to take a couple of minutes. So we can stop here. Priya, are you there?
Yeah, hello. Yeah, yeah.
Good. Good morning. Okay.
Good
So
morning.
so we use the same, just to emphasize again, we use the same methodology. If you compare the code of last week and this week, you see it's exactly the same thing. So it's nothing changed. The only thing that happened is we try to now do it for classification. And the beautiful thing about using different
Then you'll have
methodologies.
to stop your share if you want us to
Oh,
take
yeah,
over.
yeah, I'm going to stop now. So the beautiful thing about this is that it allows you to compare the different models immediately, and then you see which one will work well for your project, and then we can take that and continue the hyperparameter tuning if you want to improve the model. So I'm going to stop here. Thank you very much. Okay, Priya, you can take over. And please do not forget to, I will also attend to your questions in the chat. Yeah, thank you.
Hello, everyone. This is Najam, and we shall be doing principal component analysis. I hope all of you can hear me. Yeah, okay. So, just a moment, I'll share. Yeah, so principal component analysis is a very powerful technique for dimension reduction. Yeah, basically, what we mean is many a times we have data sets with various columns. For example, you have a data set of galaxies. So first column could have the names or the IDs of the galaxies. The second could be the masses of galaxies. The third column could be the metallicity. Fourth column could be the redshift, and so on and so forth. Right. So this kind of thing is there in all walks of life, where you have multiple features for a certain uh, object. And so suppose you have 1,000 galaxies and there are 10 different columns which give their different aspects of it. Its redshift, its position, its mass, its size, and so on and so forth. So we have multi-dimensional data, and what we are often interested in is finding out what are the most important ones in that. So, for example, if you want to understand galaxies and you want to see all elliptical galaxies, uh, we are trying to find out basically what are the important components and what are not. Okay, and principal component analysis is used for that, right? So in high dimensional data sets, like for example, you will have data sets with spectra, with images, with catalogs, and we want to reduce this dimensionality. We want to find out only those important components which are contributing for a certain thing. For example, if we are interested in knowing about only elliptical galaxies, we want to find out what are the important components? Is the mass the key factor? Is the bulge to mass ratio important? Or does the electricity change? Or elliptical galaxies they change with the redshift? Yeah, the closer Galaxies in regions closer to us, they are more ellipticals, and if you look back in time, further are more ellipticals or vice versa, right? So you want to reduce them, find out the most important factors of it. So you may reduce it to something, say, there are three different things, which really make, which is important. One is ma- mass to the the black hole size in the center of the galaxy, the redshift, or the environment, whether it's a field galaxy or it's in the central core of our cluster. So we are interested in finding out the most important components. Yeah, this is where it is used. And finally, that makes it easier because we throw out those features which are not really contributing to it being an elliptical galaxy or spiral. Okay. Uh, it's also used to remove noise or instrumental effects. And it also helps us to visualize very complex data in lower dimension. Okay, so the principal component analysis essentially is linear algebra, and and yeah, so we try to find out those components. So you arrange the data, you plot the data, and you see the direction of maximum variation, right? That becomes the principal component. And 90 degrees to that, orthogonal to it will be the second principal component, PCA2 and 3 and so on. So all these principal components which we try to find are orthogonal to each other, basically signifying that one principal component is not linearly related to the other one. And suppose if you have only two features, you have one feature and another one, and you have a scatter plot, the direction of maximum scatter will give us the first principle, and orthogonal to that will give you the second component. So it's generally just a rotation of the axis to get it. Okay. A few important things which we need to do when we do PCS, we have to scale the data because otherwise it can your analysis can get uh, biased by large numbers. For example, we are dealing with one feature which runs in, say, 10 to the power of 30, 10 to the power of 9, and so on, like the masses. The numbers are very large. And the other feature which we are looking at trying to find are, for example, the redshift. So 0, 1, 2, 3, 4, 5, 6. These numbers are small. So you have to rescale all of them so that it shouldn't appear. So obviously, if you plot it on the same scale, uh, redshift that is 0, 1, 2, 3, 4, 5, 6, and uh, 10 billion, 15 billion, 9 billion, and so on, that those will have a big scatter. So you normalize it, and in Python there are functions which normalize the data very easily. But generally, to normalize, you find the average for that feature. You subtract the individual xi from this average and divide it by the standard deviation, right? So you normalize it. And once this principal component is found, you try to find its correlation with the other features. That's the second important aspect. And sometimes you see that there can be two different features which are perfectly correlated, and hence you can throw one from the other. Yeah, it could be. Basically, the size and the mass are perfectly correct. The larger the galaxy, the masses. Then instead of taking two different ones, you can only take one of it. Okay. So that's how you reduce the dimensionality. And so here's a uh, Jupyter notebook, which we'll share with you. There's another one which we have shared. And here you are seeing that the first thing is you set up the libraries like we always do. So import NumPy as NP, Matplotlib as PLT, and now we are importing this PCA, Principal Component Analysis, from the scikit-learn, right? So scikit-learn decomposition, we import PCA, and we use this standard scalar that is to for the pre-processing of the data, what I just mentioned about rescaling and so on. And then we are using these utils of data basically essentially to read these data files, downloading it and so on. So from import utils data, import download file. So I'll give you an example how we can download the spectral data of galaxies and do some PCA with it. And from Astro Pi IO, we import fits. Yeah, so we are getting these, as we have discussed in our previous sessions, that data, astronomical data, may it be images or spectra or catalogs, being shared over FITS files. So we have to get this FITS, and here in this example, we'll be dealing with the spectra. So we'll be using that header unit where data are stored and store it in a variable and analyze. So this AstroPy IO import fits. This is to handle the fits file. Okay, so we run that and then we load. Yeah, we are now downloading this data from Sloan Digital Sky Survey, SDSS. And here's the URL. Yeah, this is an example for one of the spectra which we are looking for of a galaxy. And we specify the file path where it would be, and so it's done that. Okay. And then we are opening with fits open file path. We are specifying where it is being downloaded. That path is defined as file path, and we are from that file path we are reading. And SGU one has the flux. It has the spectra, and we are storing it in the variable flux. And we are converting the wavelengths into angstroms. Yeah, this is so 10 into to the power of SDU1 data log m. We are basically getting it into the uh, uh, in angstroms. Okay, so here we have, and then we come to the reprocessing side, and we are using this standard scalar which we had from Sky 6. We have from scikit-learn reprocessing standard scalar which we had downloaded. We are using that to essentially rescale the data. And we rescale it when we are doing xi minus x mean by standard deviation. Basically, we are converting all the values in such a way that average mean becomes 0 and the variance is 1. Yeah. So, as mentioned earlier, this is basically to uh, get rescale. Some columns may have very, very large numbers and some columns may have very small numbers. And if you try to do PCA and do a scatter plot of the data, obviously you'll be, a small change in parallax could mean more than uh, 10 to the power of 3, uh, third order of magnitude in masses. Yeah, so you rescale it, so then they all become of similar sizes, and uh, I run that, and you see that the spectra which we have read, we are plotting the spectra in blue, what we had read from downloaded in red, and after rescaling it, we are uh, what we plot, we are getting the orange one, right? So this is the scale spectrum, the one in orange below, and this is the origin spectrum, right? So now we apply the principal component analysis and to a set of multiple spectra. And for simplicity, instead of downloading many such and waiting for it, we simulate small data sets. And in this code, so we are using random seed 42 and 10 spectra. We are and number of spectra which we are making are 10. And okay, and so this is the loop in which we construct all these range and spectra. So you can change if you want to make hundreds or thousands, you just have to change the number here and do it. And when we have okay, and to set the PCA, Python makes it very simple for us. And the command is PCA and number of components is equal to how much, right? So in this case, we are trying to find only three principal components. Okay. So PCA and components equal to 3, and this is the PCA, and then you fit this data to that, and we get the variance. We are looking at the variance, and then the three variances are 0.1219, 0.1169, and 0.1160, right? This is the variance. And as you see, the principal component one has the maximum. All these are pretty similar, but the highest variance is the principal component one, which is 0.12. The next big guess is 0.1169, and uh, third one is 0.1160, right? So these are the three ones. And you see that it's very simple to filter out and see what are the variances and see what are the basic three principal components which we are doing with. Yeah, so now uh, we'll try to visualize this results of PCA which we got earlier, and we look at those components. These four components, they are called the eigenvalues. Yeah, basically an eigenvalue is if you have any transformation and we have a vector, if the transformation keeps the vector, if transformation T of V gives you, let's say, lambda V, keeps the vector as it is, only it rescales it. It can either make it big or small. The lambda is a scalar, or it can reverse, it can flip over the vector. So essentially, if a transformation which keeps a vector invariant up to scaling are called uh, eigen vectors, and this lambda value is called the eigenvalue, right? So eigenvectors are basically what we are doing is in the feature space, we are trying to find those uh, vectors, eigenvectors, and we represent the whole data set in terms of these eigenvectors. Okay, so in principal component analysis, basically it's a rotation. So your feature one is on x-axis, feature two is on the other one, and you have a scatter plot. And along you you are basically PCA. What it is doing is it is rotating these two axes such that the x-axis lies along the greatest scatter point. And the PCA2 is where the y-axis goes. It is always orthogonal. And PCA3 will be rotation in another plane and so on. So depending on how many uh, principal components you require, you do it. And our basic idea behind is in a data set which has multiple dimensions, say 10 or hundreds of them, we are trying to find out certain components. They can be 10, they can be 5, they can be 3, which represent the data total, right? So, like in vector calculus, vector algebra, in linear spaces, you, if it's a two-dimensional set, what we mean is any object can be written as a linear sum of these two basic vectors. And in this case, you are finding those eigenvectors which are good representatives of the whole data set. And we represent this data in terms of this eigenvalues, right? So, so PCA is doing this, and you see that blue one is PCA1, and PCA2 is given by these orange lines, and PCA3 is this. And if you project this data PCA space, we can see the different principal components lying, and we can see clustering. Sometimes you see them forming clusters. All principal component one will sit on one in one corner, the other will sit in some other corner. In this case, they are pretty much scattered. Otherwise, you can realize that if the a certain feature is more in one, it is the yeah. So you have principal component one and two. Similarly, you can have principal one and three and two and three, and you can see it in multi-dimensional space. And for the data which we have got, we are looking at this PCA space, and we see how the points are lying in the principal uh, um, from the PCA space. Okay, so what is the interpretation? What do we interpret from this? PCA1 basically is capturing the maximum variation of the data, right? Yeah, so this is a dominant thing, and PCA2 and 3 correspond to the, yeah, in this case, uh, the continuum shape is the is PCA1 in this example, and PCA2 and 3, they are the emission and absorption features, which also are playing important role. And this scatter plots help the outliers, how they are clustering and not. So, like I mentioned, this is used, PCA, principal component analysis, is used in spectral classifications of stars, of galaxies, of quasars. It is used in removing uh, noise, reduction of noise, and to extract features, the most important features which contribute to a certain thing is what we can extract from PC analysis. Uh, so exercises you can for practice. You can try to download more SDSS spectra. So, yeah, so the code is given here. Uh, so you have to know the URL. You'll have to change this fits file name and the site name. Yeah. and you can download and read it as it has been done. You just have to keep changing the paths and doing it. And uh, you compute the principal components and visualize the results. And for further, you have the scikit-learn PCA documentation is very well given, and in Astro ML also, this PCA spectral analysis is given, right? So this notebook is the first notebook which we shall be sharing with you on PCA. There is a more advanced notebook which has been shared, right, Priya? The one is there.
It should be there.
Yeah. So, and you can try for the uh, data, multi-dimensional data. You can change these. For example, here we are taking components as three. Suppose I take components two and run it, and see we are getting only the two principal components here, and when we so yeah, so range three, this has to be changed. Yeah, so now we are looking at only in two principal components, right? So see, basically to give a day-to-day example, what we do in astronomy is, for example, suppose you are going to buy a car, yeah, and there are various features which go into buying it. Yeah, how do we make a decision? What are the aspects which we are interested in looking at? So that space which we are looking at, like cars, one thing would be the cost of the car. How expensive is it? Secondly, it could be the other feature can be the mileage. How much does it give you per liter of petrol or diesel or whatever you're using? Third could be a factor which says what are the cost of maintenance of the vehicle, how expensive are the things where you go for services, servicing, and so on. Fourth can be the size of the car, whether it's a big car or a small car or SUV or so on. Fifth can be the color of the car, whether it's white, black, silver, etc., etc., and so on. So you have multi-dimensional parameter. Fourth can be your usage. Generally, how many kilometers do you travel per day? Fourth, whether you are using it in fifth, sixth, whether you are using it in uh, cities or in districts. So the availability of diesel or petrol or electric charging points and so on. Okay, so this is a multiple feature thing, and we have to decide which is the vehicle I want to see. And you get the range of various cars, their cost, their sizes, their all the features, the color of it and maintenance costs, etc., etc., etc. And you plot it in a multi. Yeah, if you are trying to plot this in a multi-dimensional plot, the whole thing becomes very cumbersome. There are 10 different orthogonal vectors, which are uh, features which are, it should be a high dimension. And beyond 2 to 3 dimensions, our mind can't comprehend too well. So one thing is to reduce it to get down to those features which are the most important. So it could finally lead down to when I'm suppose buying a car, it can lead down to saying the car, uh, the cost should be between say 10 lakhs to 20 lakhs, not more than that or not less than that. The feature can be availability of service centers and so on. Third is how large is my family, and hence I decide the car should be a small one or a big one. And finally, you realize that certain features like the color of the car and uh, whether the uh, seats are of leather or of cushion, and those things don't really matter. Whether it has a music system or not, whether it has a, so you reduce those dimensions to a few, and that makes it easier for you to shortlist a fewer, right? Yeah. So similarly, here when we are looking at, say, morphology of galaxies, you are looking at galaxies, you have data of galaxies, and you have, say, their masses, you have their uh, redshifts, you have their metallicity, that is the stars, those galaxies, whether they are essentially hydrogen, first generation stars, pop one star, or population two stars or three stars, and so on. And at what redshifts are you seeing, and so on. Okay. So we try to see the most important features, the correlations between them. For example, the metallicity of a galaxy may depend with the redshift. The more distant galaxies, the high redshift galaxies, will be low in metals. They are early, the stars are those early type stars, which are only burning hydrogen, right? So we are seeing them in the first stages. While you come closer and closer, you will see uh, the metallicity would increase and it will be maximum when the redshifts are near zero, right? Similarly, you may see the sizes, whether there is a dependence of size of a galaxy from the redshift, uh, and and so on. Sometimes you don't see any correlation. Sometimes you see that they are perfectly correlated, so you drop the dimensions. And this makes it easier for us to realize, and then you can understand, uh, say, galaxies better. So, in short, if I run my PC on galaxies taken from different clusters, Coma cluster, Virgo cluster, and so on, which had different redshifts, which have different environments. So one of my columns could also be how far is the galaxy from the uh, center of the cluster. And then we would realize that there are more elliptical galaxies sitting in a crowded environment, while spirals are sitting more in the field in the outer regions. And you see that there are more spirals in the early universe, and yeah, or right, a trend where they peak or star formation rates. If you look at the rate of star formation in galaxies, you see them at different redshifts, and you kind of see, right? So finally, the principal component analysis helps you pick up the fundamental, the basic components which are essential to understand a certain object well, right? Similarly, we can focus on spirals and do the same thing and see what are the basic principal components which are essential to give features of a spiral galaxies which make up a spiral galaxy, or which are the basic components which we have to focus on uh, to understand what spirals are. So to see the bulge of a spiral is important, or to see the halo of it is important, or whether the gas content plays a big role for a spiral to be a spiral, and so on. So the mass to disk, the bulge to disk ratio is important, various things, right? And it reduces your dimensions and it makes it easier to understand the data. And the same kind of uh, this PC is a very powerful technique which is used in life sciences, in economics, in business, in astronomy, and in a variety of things. So, and it's a very powerful and a very simple technique, right? So I'll stop with this. Priya will do a bit, then we'll go back to the next uh, PCA notebook which we have, which is a bit more technical. So we'll just show you the features which you should concentrate on and how to go about it.
Yeah. So thanks, Najam. I'll continue now. And I'm sorry, this was probably not in right order, but I wanted to basically talk to you all about a package called Astro ML. Okay. So let me share the screen. I need you to unshare. Okay. Yeah. So I hope you all can see my screen. Yeah. Okay. So what you see over here is this Astro ML package which has been provided by which has been provided specifically to do machine learning tasks in Python. Now, like I showed you last time, we also had scikit-learn, which I showed you, which has a lot of effective packages in for machine learning. But other than that, Astro ML is also very effective, and you may find that to be of good use. So if you actually see, it is basically it is built on NumPy, SciPy, scikit-learn, Matplotlib, AstroPy. Okay, so in Python there are certain structures. Like for example, when we did Seaborn, told you that Seaborn is kind of it sits over Matplotlib. Right, Matplotlib is the basic package over which you have scikit-learn. Similarly, SciPy, scikit-learn, etc. are the basic ones over which you actually have AstroML. So AstroML is basically it basically does fast Python representation of common tools, etc. There is a textbook which has been which is there, which is the one which has been used for AstroML, and you can read about it on this online website. You just need to go to the website astroml.org, right? Now, what happens is that if you actually see in this book, I'm basically doing this in a way to help you plan your capstone project, okay? Because now you'll all have to think about your projects, and I want to give you all ideas as to how could you actually do it, right? So what happens is that, for example, if you go through this page, you can see examples. For example, there are some data set examples. We can go in that. I think you'll have already been told about the SDSS spectra example. I think this was kind of covered. So if you actually go here, there is a location where the data set is sitting, right? The default location. And if you can actually, you go into SDSS spectrum sample. This is the code with this thing. It shows you how to fetch and plot a spectrum from the SSDSS database. Daniel today also showed you how from Vizier you can access the SDSS database. So there could be more than one maze of doing the same thing. It's not that, and often people just pick up the one that they are more comfortable with or the one that they like more, right? So there is no rule that you should do it through Vizier or you should do it through. You can do it through Topcat also. You can do it through Vizier also. You can go through the main website, the main SDSS website. If you want, you can go through that. And there are many ways of accessing the data, and because often that's what many of you all have been asking about, how do you access the data? So there's more than one way of accessing the data, and like I said, some of them have different different features, in the sense you have a different flexibility with which you can query the data, while in some of them you may just be, it's just a matter of choice that you find something more convenient or more comfortable depending on what you use. So here, for example, you have this example which is actually showing you this. I wanted to actually show you another important thing also, which will help you in your coding journey. That, for example, when you're using Google Colab, okay, this is Google Colab, and what happens is that, for example, if you AstroML also has a GitHub page, okay. If you go through GitHub, I think you'll have been explained what is GitHub. So this is the GitHub page for AstroML. And what you can actually do is that the book that I showed you, this book, right? The book that was there in the previous screen, this one, right? This has various chapters. You can see the table of contents over here, which is, okay, I'll have to open it and show you. So here's the table of contents for that book, okay? And what basically is there is that code has been written for various things. For example, you can see chapter number 8 is on regression model fitting, 9 is on classification, 10 is on time series analysis. There are various things like that, right? So there is a corresponding GitHub page which actually has the code to the stuff, for the code which is there in this thing, right? So what one can do is through Google Colab, you can actually upload, for example, you say upload notebook, and you can upload it from the GitHub page, right? So I just did this 2 minutes ago, so I will redo it now for you. Supposing now you say the GitHub page you are looking for is AstroML, and you search, right? Let's say you search, and here see it's showing you all the Python notebooks which are available on the GitHub page of AstroML, right? Now you may choose a certain chapter. Let us, for example, take I don't know, central limit theorem, or we can take, for example, Gaussian mixtures, for example. Let's say you take Gaussian mixtures. So you open this Python notebook and you do it through this, right? So what I would suggest is that if you actually go through this thing, through the AstroML page, you will see that there are various things. This is the GitHub page. This is AstroML. You will see that there are various things being mentioned: data sets, unsupervised learning, clustering, various things which have been described in the user guide, right? So for example, we spoke about clustering last time. You may go to unsupervised learning and, so for example, clustering, chapter 6, 2-point correlation function, or whatever you may like. And you can see that here is the code for the thing, right? And this can be directly imported onto your Google Colab, okay? I hope all of you all are aware that, for example, here you can see, I won't go into the details, but we already last time spoke about Gaussian mixtures. That supposing you have a distribution of points and you assume that there's a Gaussian mixture in them, you use that to find out. If you remember, I showed you the example of membership in star clusters and how to separate the cluster stars from the field stars, we can use Gaussian mixture modeling, right? So you don't need to get too worried about all these other things. This is, it's okay. But you basically need to import the important this thing. If you see, I'm basically generating X using some random sample, right? So I'm generating the data, which is over here, random say normal distribution. And then I, for example, if I plot this stuff, right, I can plot it, and you can see here I'm getting the plot of all the distributions, right? So even if many of you all are not experts on Python coding, you can often, use the codes which are already available on those GitHub pages. And what you basically need to do is to tailor it for your use, right? So for example, if you're using it for a certain sample, maybe you're using it for quasar data or galaxy data, whatever. This thing is a synthetic sample which has been generated using random numbers. If you see over here, you're using random numbers to generate it. But here, instead of this, you could actually have your data, one of the data sets we've spoken about, okay? And for example, if you do this and you plot this, I wanted to basically also tell you all that within Google Colab, a very useful thing which I often tell students about is you can have a code cell. And for example, it basically uses Gemini AI, okay? So Gemini AI is incorporated into GitHub, right? There are many other AI tools which are also available for coding, and it's a good idea to actually use these tools for coding, the AI tools which are available. So what happens, for example, in Google Colab, I can, if I've run this thing, I can always generate some code. For example, I don't know how to write the code. While you are doing the code, you can click on generate with AI, and you can say, for example, yeah, look at this, print a hello world. For example, if you want to do this, you can say this. Let's say you want, okay. Or let me just say plot a straight line for data provided, for example, right? So you say this, And what it actually does is it actually writes you the code for a straight line. So for example, look at this code, I'm sure you can understand it. Import matplotlib.pyplot_splt, import numpy. It's defined the x line is a numpy array between -8 and 8, and a y line which is a numpy array, which are the example points. You can adjust it as you need. This is your thing. And you then say you plot a PLT plot, X line, Y line. Color you are defining with red, line style is whatever, label is straight line. And say if I run this thing, I can actually plot a straight line, right, using this data. I can obviously, the idea is that in present day coding, what is required is you do not need to remember all the commands to do everything, right? Even I don't, nobody remembers the command. What you need to know is what is called question at the prompt. This is the prompt. What is the question, which is often even called prompt engineering, where you actually decide what is the more specific your prompt is, the better will be the output and the better you can run on it. So you run this plot straight line, for example, and you got this code and you accordingly tailor it for your requirement, right? So for example, if you, this is for data provided. Now you may, for example, data provided in a CSV file, for example. Okay, I have the data in a CSV file. So I'm going to run this again. And then now it's going to actually show me that if I have a CSV file, you can see data frame pd.read CSV, your data.csv, and now it's basically going to, a CSV file, if you remember, is comma separated variable. So it's going to pick up a file which has X in one column, Y in one column, and it's going to use this data to actually fit it. And instead here, what you can see, it's fitting it to a polynomial. Okay, it fits it to a polynomial and it does this thing and it plots it accordingly. I won't run this because basically if you run this, you need to have a CSV file, right, with your data. But in short, I wanted to just show you that now when you start working on your capstone project, in case if you're working with, for example, Google Colab, please use the generative AI, right? The Gemini AI, which is available on Google Colab. So while you are trying to build up your code, right, in case you have any questions, instead of Google searching for what is the code, in Google Colab itself, you should query whatever you want. And often Google Colab recognizes what kind of code are you running, right? So often it even prompts you very well as to what is the things you may require or how can you actually build up on the code you have, right? So I would suggest that most of you all try to use Colab and try to use the prompt to actually write your notebooks and build the code of your liking, right, of whatever your requirement. Obviously, if you have any questions, you're most welcome to ask, right? Now here we are continuing with plotting of these different distributions, and here it has been used to actually divide it into class 1, class 2, class 3, and using some other SciPy functions. I'm not going to go into more detail with this, but you can actually have a look at this. So similarly, what happens in what is available on the GitHub page, I'll show you over here. You can see that the GitHub page has chapter 1, 2, 3, 4, 5, 6. 6, if you remember, is the one we were looking at. For example, if you go into chapter 7, you will see that this is what Najam just spoke about. This was dimensionality reduction. And this very notebook is what I've given to Daniel, which is sitting on your GitHub page, which is basically on dimensionality reduction. Same, what we call principal component analysis, which Najam sir just spoke to you about. So for example, this is the one. So again, I can go to Google Colab and I can say upload notebook from GitHub. I'm looking for AstroML. And what was that chapter? I forgot. That was chapter 7. Acha. So I need chapter 7. Let me look for that. And here. So dimensional reduction, I can open this file directly. And now I'm directly accessing the Python notebook from the GitHub file, right, from the GitHub page. Now you can see that this is a much more Najam sir explained it to you in a much more understandable fashion. If you see, this one is more a little more textbooky because it's part of the textbook, but it basically explains principal component analysis exactly like sir told you that you should rotate your axis to align a correlation, right? Think of a three-dimensional plot. It looks three-dimensional to you, but if you turn it around, maybe you can get a straight line if it's in a certain angle. And accordingly, then you can make it a two-dimensional thing instead of it being a three-dimensional one. Right? So this is the principal component analysis, which is this thing. I think to save time, I'm not going to run it, but I am going to, I'll leave it for you. It's available on the GitHub page. You can see over here that this code basically generates random data and then looks for in which way should you turn it so that you can this thing. The good part about this data set is that they have actually used SDSS spectra, okay? Because we have somehow not yet spoken in this course about spectra, and spectral analysis is also something very, very important. So if you actually look over here, this is the SDSS spectra that they've used, right? Which you can see over here, the wavelength versus this thing. And then it actually used principal component analysis to reconstruct the spectrum and get these various features, which you can see over here. It calculates, Sir spoke to you about eigenvalues. It calculates the eigenvalues, gives you all these things, and with this you can continue with this thing. There's some more things, PCA with missing data. There are many things of how do we actually deal with missing data. Good, this thing. Oh, there are some questions in this thing, PCA. Okay, we'll take that.
Should I answer that?
Okay, that you can just answer that.
You just mute it. Yeah, so there is a question about PCA space. Analog will be similar to phase space. Yeah, basically it is. Yeah, but see, it's not phase space usually is coordinated velocity space. In physics, is taken as space space. Here, the features can be, they needn't be positions and velocities, but they can be other features. It could be metallicity, it could be redshifts, and so on. So, in certain cases, when we are dealing, it has to do with dynamics aspect, then yes, it comes down to the space space, but not in general. Okay. Second thing, Nasir has asked is should PC1 and PC2 be absolutely independent from each other? Yeah, they have to be orthogonal. PCA1 and 2 are constructed in such a way that they are absolutely perpendicular to each other. Yeah, they are. So there is no correlation between them. Right? So when you have two objects which are perpendicular to each other, you can't write one as a linear combination of the other, right? So they are orthogonal. And all these PCA 1, 2, and 3, we are basically trying to find uh, orthogonal components which will capture the whole space, the whole feature space, and hopefully in a smaller dimension because that's one of the ideas of doing PCA. What is a huge spike in the galaxy spectrum in blue?
One of the spectral lines is there.
I know those are spectral lines,
What is the wavelength?
and those lines indicate these are peaks or so when there is an emission line, then it comes up at a spike. So depending on what angstrom you are seeing, it shows this presence of that element, right? So when you look at spectra of a galaxy or of a star, you see you see peaks, and the strength of the peak will give you the how much of the abundance of it.
Okay, okay.
So where is it appearing indicates the presence of
It's the Sodium D line.
Yeah. So it's whether sodium line, whether it is hydrogen line, depending on where it's appearing. Here it is appearing at
5,800 angstrom.
5,900 angstrom.
5,800 angstrom.
5,800
So it's the
angstrom. So
sodium D line.
it is basically sodium D line, right? So these spikes indicate emissions coming from.
And it's very important because it will give you the redshift of the gas.
Yeah. So, and then if it is shifted from that location, right, it tells you also the velocity with which the object is coming towards you or not. So at 5,800, like you see here, you have sodium line, emission line, but if it gets shifted towards the red end, you see that object is moving away. If it is shifted towards the blue one, it is approaching. Okay, so this spectra is very important. It not only tells the chemical composition of the object, what are the elements present there, but it also gives you the redshift and it gives you velocities and various things. Okay, what else? How could you show how continuum estimation was done on SDSS spectra?
Yes, so I'll this
Yeah.
thing.
That's it.
Yes, so Vibhav, you have a question on how continuum estimation is done on SDSS spectra. So generally that is done by fitting it. You see the profile, right, which is there in this notebook. But what is typically done is you actually fit it to some function, right? And using that, you actually kind of cut off the continuum component. Pratyash has been asked the notebook for capstone project should be descriptive. Are we supposed to give a presentation? Yeah. So ideally speaking, the notebook should be like the ones that we've been sharing with you, because that is the typical way to write a notebook. You have some code boxes and you have some text boxes, right? So in the text boxes, you can add all the description of the project and what do you want to do, and exactly like we've been sharing the notebooks with you all, right? So in your text boxes you can add a description about what exactly is your notebook doing, etc. And then in the code boxes you can have the code being run, right? So it will all be part of the what do you say, part of the same notebook. In the notebook itself you should have all these things sitting in there, right? The text as well as the listing, exactly like how these ones are written, right? These notebooks which we've been sharing with you all, typically you put the text along with the code so that you can have them all together, right? So I'll go back to that, and you can actually see in the AstroML GitHub page, this was chapter 7. Then there was chapter 8. There's chapter 8, which is basically about, what was it? Okay, chapter 8 is regression and model fitting, right? Which is a very important thing which we do in Astro, regression and model fitting. So you can actually, there are various notebooks over here. For example, there's one, this one is a basic regression, this thing. I'm sorry, I'm little running through this thing, but basically my idea is that if you, what do you say, you access these notebooks through Google Colab, then you can run these notebooks and accordingly, try to understand them. Similarly, these notebooks, since they are already available, right? A simple thing is that if you can just think of a different science case, right? Or what science case could you do with a certain data set? You can accordingly, what do you say, tailor these notebooks or kind of adjust them, or what we call rewrite them or whatever for your purpose, right? Because that's how we basically work on that, because one big advantage of Python is that there are very large number of libraries and large amount of code already available online in Python, right? For example, you want to do Gaussian mixture modeling. The code is already there. So these notebooks are basically showing you an example of how is it being used. What you need to think about is what exactly do you want to do in your project, right? Supposing you want to work, some of you all have been writing to me also. Supposing you want to work on exoplanets, or you want to work on stars, or you want to on galaxies or quasars, or whatever is the topic that interests you, right? If you accordingly understand that your project is a question of regression, for example, or it is classification, or what is the clustering, what is the basic what do you say, a technique that you're going to use for your project, you can actually use these notebooks as basis, right? And then you can kind of adjust them for your requirement, right? So for example, look at this one. This is a regression one, simple regression one, which is easy to do. And basically what does it does, it models the distance of 100 supernovae as a function of redshift. Okay, so that's what they're doing. If you can see this over here, I can, if you want, I'll get it up from this thing. This is chapter 8. So in GitHub, you can see, I can open it. I can open the notebook. And where is chapter 8? Oh, sorry, I'm opening from GitHub. And let me look for chapter 8. So this was the chapter 8. This is the regression one, yeah. So this is the regression one, which is the same one we were looking at. So you can see here they're using simulated data. So again, like I told you, model the distance of 100 supernovae. So you use this, we run it, and one minute, I have many sessions running, so I'll just stop these. It didn't close those sessions, so I'll just say close. Okay, so now here I have this, and what happened? Okay, why is it coming shifted? I don't know. Is it now coming better? I'm sorry, I don't know why is this notebook coming down. I'll stop share and let me reshare. Okay, now is it better? Now it's fine? Okay, very good. So now you can see there's AstroPy has cosmology. I'm going to use that, and I'm going to use these things. Okay, so you can have a look at this. Similarly, let's get back to our AstroML thing. You see there is one, this thing on AstroML of using the SDSS Great Wall. What is the Great Wall? Is that you basically, if you use SDSS data, I won't go into details, but you can actually, when you plot it, you actually get something called a Great Wall, okay, which is a certain region where you have this high density of galaxies. Now you can think of how you can use this data and analyze it. So you can see that this is the input data, for example, of the Great Wall. You evaluate with Gaussian, this is a kernel density estimator with a Gaussian kernel, and you can use that to actually fit a Gaussian. You can see this Gaussian over here, and the Gaussian tries to fit it and actually get the parameters of this thing. Again, you can do it even using nearest neighbor. We've spoken to you about nearest neighbor method. And here what they've done is that they've compared the results for the Great Wall using various methods, using Gaussian mixture, using nearest neighbor, and using this one, exponential top hat, etc. Right? So you can do it like that. You can also, 1 minute, I'm sorry, but this is the chapter 8. If you go through chapter 9, you'll see chapter 9 is on classification, and actually this is the one which I shared with this thing on deep learning for classifying astronomical images. We unfortunately do not have the time to run it today, but you can actually have a look at it, and this will basically, if you see here, this is the code, right? So the code is provided over here. You can actually use this for classification, right? The classification could be of different kinds, and how you're actually wanting to classify. Okay, yeah, that's the classification problem. Okay, that's the notebook. So you can have a look at this. And so what I would advise you is you step back and first explore a little bit as to what exactly, which topic do you want to work on in astronomy. In this course, we could not cover astronomy topics because we were focusing on data analysis and things like that. We did not do anything in this thing, but there are plenty of resources available on the net. So I would suggest you have a look at the resources available, and you can send us questions also. Decide on what area you want to work in, right? And then what are the, when you see that, you can actually think as to what are the science cases that you would like to study, right? You may even look for papers, published papers, which have something. Supposing if SDSS data interests you, or some whatever it is, you can look for papers which are available online. See the kind of work that people have done. See if you can do some kind of an improvisation or a variation of what has been done in a paper, right? So the paper can guide you, and then you can think of what variation and all you would like to do to it, and accordingly spend some time on deciding your science case, because that is the most important thing. Data analysis is important, but obviously what is more important is what are you trying to study, right? So focus a little bit on your science case. Once you decide on your science case and what exactly are you going to query or question, then you can think about the methodology that you will apply, right? What is the code you will use and how will you build up onto your notebook, right? So I'm not going to go into more details with this, but please have a look at the the various things. You can see AstroML. Here is 8 on regression, 9 on classification, and 10 on time series analysis. You've also been taught some stuff about the time series analysis, and see if you can actually study something in here. So you can see over here, this is for that, and how could you actually, so for example, if you want to do a chirp search, if there's somebody interested in grav waves, for example, you may actually use some you may use some data to actually look for that, right? And accordingly pick up your thing. So I will stop over here, and let's just look at questions. Okay. Thanks. So somebody asked for link for Astro for ML, and yeah, you just have to Google it. Don't worry. Even if you want to find the GitHub page, you just Google it. You'll find. So thank you. Who was this? Who answered the question? Let me see. Yeah. Who was it? Mulchand. Yeah. Thanks. Yeah. Just search on Google and you find it. Yeah. So. Yeah. Yeah, so Mulchand, yeah, running the AstroML data with Colab is this thing. And thank you. Yeah, thank you, Mulchand. Yeah, very good. So please try to run it. And, as you have a good thing, even in Colab, is it actually, if there are errors coming, it actually tries to explain the error, right? Which is also quite a fun thing, because let me just show you that, for example, if you, 1 minute. I'll just say share. Why is it not sharing? Is something coming on the screen? Is something going to share? Okay. So I'll go back to this, and if you actually come here, if you see here, yeah, if you make a mistake, for example, if I say, let's look at this window, I'm saying import numpy as this thing. Let me just call it numpy O, for example. Okay, and I run this, and you can see it's giving me an error immediately. It says there's no module called numopy, right? So here what happens is, it often, Google Colab even explains the error, right? And often gives you a possible solution for the error. For example, it says, look at this, it looks like there's a typo in the import statement. The module numopy does not exist. The correct non-module name is numpy. I will fix this for you. So I say accept and run. So now see, so sweet of it, it actually corrected it for me, and ran the code over here and made it import numpy as np, right? So you can actually often use the if you have errors, please use Gemini AI, it will actually try to judge what is the error and give you a solution. Obviously, not always is the solution correct, but at least it gives you something to start with, right? So, in that way, it is helpful, definitely. It's like a friend around there who's going to help you to solve your problems. Presentation, that Daniel will answer whether our presentations required, because we have so many of you. I don't know how we're going to have like 100 presentations. So Daniel, you tell us whether these people have to do presentations or no.
I think we've said this a couple of times. There's no presentation. Your presentation should be in your Colab notebook. So
Okay.
you should write everything you want in your Colab notebook. Make cells. It allows you to do markdown and code. So we should have all of those things: your problem, the title, the problem, data description, your analysis, your insights, the results you generated. Explain everything in the Colab notebook. I remember in the week 4 when we shared this, or so week 3, I did show you a couple of examples. If you look at the notebook that's been shared to you, you see it's always in the form of presentation. If you make the plot yourself, we can see the plot in the notebook because it's going to display. If you do analysis, it is going to display. So everything should be in a Colab notebook. Every single thing, just like the notebook that Priya just finished sharing. You can see it has both text and images. So please, I think I've been answering this thing almost every day on the Slack channel, and I think we need to, because at this point, I believe you should be rounding up your presentation, your Colab notebook for this. Please, for the final time, everything should be in a Colab. And if you are confused, go to the capstone link that was shared earlier, or go to GitHub. You're going to see the link there. Open it and read the instructions again. Thank you very much. So on this note, I think we'll call it today. I'm not seeing any new questions in the chat. Yeah, the Colab that Priya shared, they are all available online. You can open them and also open them on Colab, the Astronomy. You can also download the book. I think it's also for free. You can open it yourself. You can read the notebooks, and definitely there are a couple of things to learn: how to do modeling, how to do statistical analysis, and also the ones that apply to astronomy. You can find anything that's related to your use case there. Okay. In the absence of any other question, we can end it here this morning. Once again, thank you for joining us. Thanks to Priya and Najam for the wonderful presentation this morning. Some of you don't know that Priya, this time is not convenient for them. They are awake late in the night instead of sleeping to provide this resource for you and also put you through. So thank you again for joining us. We'll reconvene in the evening. For those whose time is not, I guess, for people in the other part of the world, so in the western part of the world. So we'll meet again, say in the next, I would say probably, what's the time now? This is 11 a.m. here. So roughly in the next 7 hours. So thank you all for joining us today. And please, this is going to be our last lecture. If you have any questions, do ask in Slack. If you have any concerns, do ask in Slack. And please work on your notebook. And the information about the whole submission have been shared. Label shared it, I think last week or earlier this week. So please go through that document, read it again, and try as much as possible to do that before the deadline and submit. Thanks very much, guys, for joining us. We convene again in the evening. Not for you, but for those who are in the other parts of the world. Bye, everyone.
Bye-bye. Bye.
Bye.